Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are here for our lecture number 15 for the subject of operations management. I am Dr. Arshad Zahir, your course instructor for this subject of operations management. I have delivered 14 lectures up till now about this particular subject, and I have introduced you some mathematical techniques, some iteration techniques, that how we can achieve our objective functions. Most importantly, we have taught about the linear programming techniques. Initially, we used that graphical method of solving the linear programming problems, and then we used the simplex method in order to solve the related problems. And you are now well aware that we have the two methods, that is big M method, which is also known as penalty method, and the other one is two-phase method, which can be used in order to solve those linear programming problems with the help of that simplex method. So class, now you have the idea that how we can formulate our real life problems in the form of equations, and by converting the real life situations into the equations and inequalities, how we will be able to find the optimal solution. Now these techniques are so important for all of the operations managers that if they are not well aware of these techniques, it will be very difficult for them to take some important decisions in their production settings especially. So it is very important for all of the managers, whether it's the operational managers as well as the other managers, that they should be well aware of some of these mathematical techniques that help us to achieve our objective functions. Now class, in our previous lecture we discussed in detail two-phase method of simplex method, and I introduced you some important steps that how we can solve the similar problems by using that two-phase method. In that particular method we use two phases. First of all, we enter into the phase 1, and then we enter into the phase 2, and there are the particular steps and there are the particular concepts in each of this phase. Initially, again, what we do, we convert the different real-time situations and the real-life situations in the form of equations and inequalities. That is, we'll have to formulate our objective function, and that is, we'll have to convert our profit function or cost function in the form of equations. Then again, every organization have the limitations and the constraints. We'll have to convert those constraints in the form of inequalities or in the form of equations. And again, when we use this two-phase method of simplex problems, we'll have to convert these inequalities into the equalities by using the slack variables or surplus variables. So after using that slack variables and surplus variables, we'll have to make a try for the initial solution. But sometimes when we use this initial solution method, what happened that sometimes we have a sort of contradiction or a sort of violation, that is maybe in the form of non-negativity constraint violation, or that may be a basic mathematics rule violation. So in order to deal these violations, what we do, we introduce initially some artificial variables to our equations so that we can have the proper initial solution. Now class, what we did in the first phase of this two-phase method, we introduced a new artificial objective function, which is generally represented by f. And what will be the value of that artificial objective function? That will be obtained as the sum of all the artificial functions or the variables we have introduced in our equations in order to deal with the different violations or the contradictions. So that is the very important step in the first phase, that we'll have to introduce an artificial objective function along with our original objective function, and then we'll have to compute the values of the different artificial variables from the different relevant equations, and then we'll have to put these values of artificial functions in the new formed artificial objective function, and we will convert this artificial objective function in some homogeneous form. So again, we can rewrite our original objective function, our artificial objective function, as well as our different equations which are actually being made in order to find the initial solution. Again class, we will use the similar rule that you'll have to find out that what is the number of variables and what is the number of equations available, and we will find out the difference between that number of variables and the number of equations, and this particular value will tell you and give you the idea that how much variables will have to put equal to 0 in order to find that initial solution. So after putting these arbitrary values of the different variables to 0, we can find out the values of other variables, and we can have some initial solution. Then in the next step, what we'll have to do, we'll have to formulate an initial tableau by putting the coefficients of all of these objective functions, that is the original objective function as well as the artificial objective function, as well as all the coefficients of the different equations. So after placing all of these values at the relevant position in this initial tableau, we'll have to check the condition of optimality, that is all the coefficient values of the artificial objective function should be negative. If there is a single value we have as the coefficient of artificial objective function, then it means that this initial tableau will not give you the optimal solution, and we'll have to reformulate another table. In the next step, we'll have to identify the maximum positive value as the coefficient of artificial objective function, and this particular value will give you the idea that what is our pivot column the coefficient, and that pivot column coefficient will also indicate you and will help you to identify that what is your leaving variable. Actually, the non-basic variable with respect to the respective pivot column is your entering variable. After identifying your pivot column, you'll have to identify the pivot row. And how we can identify the pivot row? We'll have to divide the right hand side column values with respect to the corresponding pivot column values, and so we can get the different ratios for the different values. And in this particular step, we will just ignore the negative values or the infinity values. We will just take into account the positive values, and then we will have to find out that what is the minimum ratio, and this minimum value will help us to identify that what is our pivot row. And then we'll have to look for our pivot number, and this is the number which lies in a particular cell at the intersection of pivot column and pivot row. And the pivot row also gives you the idea that what is your leaving variable. The basic variable corresponding to the respective pivot row is your leaving variable. So after doing all of these steps, now we are in a position to recompute our new pivot row and recompute all the other rows by using the different formulas. Again class, in order to find out the new pivot row, the formula is that is the new pivot row is equal to 1 over pivot number multiplied by old pivot row, and the formula for calculating any other row which is other than the pivot row will be equal to old row minus pivot column coefficient multiplied by new pivot row. So by using both of these formulas, what we can do, we can compute our new pivot row as well as our new other rows. So after doing these sort of calculations, we'll have to again formulate our next table, and we'll have to place these new row values in this respective table. And again, this is a sort of loop, and this process will be continued until we have the condition of optimality. After we have the condition of optimality, that is all the coefficients of our artificial objective functions are either 0 or they are negative, then we will be in a position to enter into the phase 2. And how we will enter into the phase 2? By using this particular method, what we will do, we will just ignore the artificial objective function values, and we will also ignore the artificial variables that is being written as a column as the non-basic variables. So we will omit the respective columns, and we will omit the new artificial objective function, and we will reformulate our W in our phase 2. Again class, in this phase 2, now we will have only one function, which is actually our original objective function, and with some basic variables, and again with some non-basic variables. Again, out of this table we'll have to check again the condition of optimality, and again we'll have to repeat the similar steps. That is, we'll have to identify pivot column, pivot row, pivot number, leaving variable and entering variable. And after doing these sort of steps, we'll have to continue these steps until we have some optimum solution. And finally, after we get the optimal condition in a particular table, we can always find out the relevant values of our variables, which can help us to maximize our objective function. So these are the different steps which are involved in this particular method of two-phase method of simplex problems. And now class, we have discussed the two-phase method. We have discussed big M method, that is usually referred as penalty method. We have also talked about the graphical methods of solving the linear programming problems. In our today's lecture, we will discuss some important situations in which we may not be able to find some optimal solution, or sometimes we may have some infinite solutions. So these are the special cases, especially with relevance to simplex method of solving the simplex method problems. So in this particular lecture, we will discuss these special cases. There are 4 special cases in the use of the simplex method. The first case is the degeneracy case. Now students, what is the degeneracy case? Degeneracy की situation एक ऐसी situation होती है कि जब हम simplex method को use कर रहे होते हैं, and we are trying to find some optimal solution. तो as you know कि इसमें हमें बार बार loop चलाना पड़ता है, बार बार table बनाने पड़ते हैं. तो degeneracy situation is this sort of situation कि ये loop जो है, ये step हमें बार बार करने पड़ते हैं, and still we may not achieve some optimal condition. So degeneracy का मतलब ये है कि ऐसी problems होती हैं कि जिसमें हमारे steps जो हैं चलते रहते हैं, looping हम कर रहे होते हैं again and again, but still we sometimes are not able to find some optimal solution. So ये जो looping हो रही होती है, या जब हम different steps use कर रहे होते हैं, तो इसमें आपका objective function जो होता है sometimes वो repeat हो जाता है. For example, हमने 3-4 दफ़ा table बनाया, और 3-4 table बनाने के बाद again आपको वही वाली objective function की value मिल गई जो इससे पहले tables में हमें मिल चुकी है. So this is a situation which is particularly with respect to that degeneracy solution. इसको हम sometimes cycling भी कहते हैं कि एक cycle चल जाता है, but in that particular cycle हम जो है अपना particular जो optimal solution है, we could not be able to achieve that optimal solution. So this sort of situation and this sort of case is referred to as degeneracy case or degeneracy situation. Then another important case with respect to that simplex algorithm, that is the alternative optimal solution. Now class, this is a particular solution in which sometimes we have some infinite number of solutions. Now اس کیس میں کیا ہوتا ہے کہ ہم اپنے ٹیبل بنا رہے ہوتے ہیں لیکن ہمارے پاس ڈفرینٹ انفینٹ سولوشنز ہوتے ہیں جو آپ کو سم ٹائمز سیم ویلیو آف فنکشن دے رہے ہوتے ہیں. سو ان دس پرٹیکولر سچویشن اینڈ ان دس پرٹیکولر کیس وی مے ہیو دا ڈفرینٹ ویلیوز آف objective functions which are actually same by using the different combinations of our decision variables. So in this case actually we have some infinite number of solutions. So this is the particular situation when the operations manager will have to decide on his own experience and observation that what is the or what may be the best combination of the decision variables so that they can achieve the objective. Then class, there is another case that is usually referred to as unbounded solution. Now اس کیس میں بھی if you remember جب ہم ٹیبل بناتے ہیں تو اس میں ہم different ratios نکالتے ہیں by dividing the values of right hand side column with respect to the corresponding pivot column. So اس میں ہم نے ایک کنڈیشن کو ڈسکس کیا تھا کہ اگر یہ ویلیوز نیگیٹو میں ہوں گی یا یہ ویلیوز انفینٹی میں ہوں گی تو اس کو ہم اگنور کر دیتے تھے اور وی اونلی ٹیک ٹو اکاؤنٹ دوز ویلیوز آف ریشیوز وچ آر آلویز پازیٹیو. بٹ دیر مے بی دی کیسز کہ جب ہم اپنا ٹیبل بنا رہے ہوں اور یہ ریشو کیلکولیٹ کر رہے ہوں کہ آل دی ویلیوز آر نیگیٹو اور انفینٹی. So in that particular case we will not be able to solve that particular problem by using this simplex method. So this sort of problem is sometimes referred to as unbounded solution. اس کو ہم unbounded اس طرح سے کہتے ہیں کہ کسی ایک ویریبل کی جو سولوشن سپیس ہے وہ انفینٹ تک چلی جاتی ہے اور اس کی ویلیوز انفینٹ چلی جاتی ہیں اور آپ کی جو نان بیسک ویریبل ہے اس میں سے کسی ایک کی ویلیو جو ہے وہ آپ کے زیرو آ جاتی ہے. سو دس سارٹ آف سچویشن از سم ٹائمز ریفرڈ ٹو ایز unbounded solution. Then in another special case which is usually referred as infeasible solution. Now infeasible solution is referred to the situation in which we are not being able to find the optimal solution. Now students, sometimes آپ کے کچھ کانسٹینٹس ایسے ہوتے ہیں کہ ہم سب قسم کے یا ہر قسم کے کانسٹینٹس کو فلفل نہیں کر سکتے. سو دس از دی سچویشن when we will have that infeasible solution, that we will not having any choice or we will not having any method or alternative to find the optimal solution satisfying all the constraints. So there are some situations in which sometimes it is not always possible for the operations manager to fulfill all the available constraints. So this particular case is referred as infeasible solution. So let's discuss all of these three or four important cases. Students, in cases کو میں اس طرح سے ڈسکس کر رہا ہوں کہ as we have discussed many problems by using and by solving these problems by the graphical method and by using that big M method or by two-phase method, but اگر آپ کوئی پرابلم سولو کر رہے ہوں اور وہ پرابلم کسی بھی میتھڈ سے سولو نہ ہو رہی ہو یا اس میں کوئی پرابلم آ رہا ہو تو یو مے ہیو ان مائنڈ دیٹ اٹ مے ریفر ٹو سم آف دیز کیسز. سو please don't scare if you are not being able to solve a particular problem by using any of this method, because in reality it is not always possible to solve all kinds of problems by using these linear programming techniques. This technique also have certain limitations. So these cases which we now are discussing in this particular lecture actually refer to some of these situations. So we will discuss each of these cases in detail. Degeneracy basically refers no improvement in objective. Now what is meant by no improvement in objective? Again, this is a sort of situation when we are formulating and reformulating the different tables again and again by using the either method, that may be the big M method or that may be the two-phase method, but even then we couldn't be able to find any improvement in our objective function. اینڈ اتنے اسٹیپس کرنے کے بعد بعض دفعہ وہی سچویشن آ جاتی ہے جو ہم پہلے کر چکے ہوتے ہیں, یا وہی ٹیبل آپ کے سامنے آ جاتا ہے جو ہم پہلے بنا چکے ہوتے ہیں. سو دیٹ پرٹیکولر سچویشن از یوزلی ریفرڈ ٹو ایز ڈیجنریسی. So what is a degenerate solution? A solution of the problem is said to be degenerate solution if the value or values of basic variables become zero. So in this particular case of degeneracy, sometimes we will have those values of basic variables equal to 0, and it will give you the idea when you have this sort of situation while solving the problems. So you should have in mind that this may be the case of degeneracy problem, and it occurs due to the redundant constraints. And redundant constraints again وہ constraints ہوتے ہیں جس کو sometimes ہم fulfill نہیں کر رہے ہوتے, اور sometimes یہ constraints جو ہے صحیح طریقے سے formulate نہیں ہوتے. As we have already discussed that as a very first step of solving these sort of problems, first of all what we will have to do, we will have to take the particular information from the organizational scenario, and we'll have to convert that particular situation in the form of inequality if we want to represent our constraints especially. So sometimes یہ جو constraints ہم بنا رہے ہوتے ہیں یا اس کو انیکولیٹیز میں چینج کر رہے ہوتے ہیں, تو یہ اپروپریٹلی ہم چینج نہیں کرتے یا اس کو کنورٹ نہیں کرتے انیکولیٹی میں. So that may be a sort of redundant constraints that we have not been able to formulate our constraints rightly. This is in itself not a problem. So if you face this degeneracy problem, so it is not your fault, but that is the sort of situation which anyone may face. But making simplex iterations form a degenerate solution give rise to cycling, meaning that after a certain number of iterations without improvement in objective value, the method may turn back to the point where it started. So students, as I have just discussed, کہ جب یہ ڈیجنریسی کا پرابلم آتا ہے when ہم جب ٹیبل بنا رہے ہوتے ہیں تو آپ کی ایک سائیکلنگ سٹارٹ ہو جاتی ہے, آپ کے ٹیبلز اگین بن رہے ہوتے ہیں, لیکن آپ کو جو آبجیکٹیو فنکشن ہے وہ میکسیمائز نہیں ہو رہا ہوتا. سم ٹائمز آپ کی آبجیکٹیو جو فنکشن کی ویلیوز ہے وہ ریپیٹ ہو جاتی ہیں, اور وہ ٹیبل جو ہمارے پاس پہلے ہوتا ہے اگین دیٹ ٹیبل may also be repeated in the similar form. So this is a sort of situation جس کو ہم کہتے ہیں سائیکلنگ سٹارٹ ہو جاتی ہے, اور اس پرٹیکولر سچویشن ہی کو ہم کہتے ہیں دیٹ از دی ڈیجنریسی پرابلم, اینڈ we will have the degenerated solution in that particular case. So let's take an example in order to better understand the special case of degeneracy. Suppose we have the function f is equal to 3x1 plus 9x2, and we want to maximize this function, and this function is subject to the different constraints, that is x1 plus 4x2 is less than or equal to 8, and x1 plus 2x2 is less than or equal to 4. Now again class, I will not solve completely this particular problem, because now you must have sufficient practice of solving these problems, that how we should add the slack variables, surplus variables, artificial variables, and how we can find the optimal solution either by the two-phase method or by use that penalty method or big M method. So again, let's discuss this particular case. So as a first step, you know that you will have to convert these inequalities into the equalities by using the different slack variables. In this particular case, we have introduced the two slack variables, that is S1 and S2 for the first constraint and for the second constraint respectively. And again, we have the non-negativity constraints as x1, x2, S1, S2 greater than or equal to 0. And again, if we try to find out some optimal solution, we can put the values of x1 and x2 is equal to 0. So if we put the values of x1 and x2 is equal to 0 in the above equations as well as in the objective function, we will get the value of f is equal to 0, s1 is equal to 8, and s2 is equal to 4. So this is actually our initial solution. Now again class, after finding out that initial solution, again what we do, we'll have to again formulate our initial tableau. And again in the initial tableau we have some basic variables as well as we have some non-basic variables. In this particular case our basic variables are S1 and S2, and our non-basic variables are all X1, X2, S1 and S2, which is written in the uppermost row in this particular table. So again we'll have to put the coefficients of the different equations as well as the objective function in this particular table. So our first equation is x1 plus 4x2 plus s1 is equal to 8. So class, we have put these particular values or coefficients here in this particular table. So this is the coefficient of x1, this is the coefficient of x2, this is the coefficient of s1 in the first equation. As there is no s2 in the first equation, so we will put s2 equal to 0, and again on the right hand side of first equation we have the value as 8. So again we will write that 8 here in that right hand side column. In the similar fashion we will put the coefficients of our second equation in this particular table, and again we will convert that objective function in some homogeneous form, that is we should have the constant value on the right hand side of the equation, and all the other values should be taken to the left hand side of that particular equation, so that we have the objective function in some homogeneous form, and we are able to put those coefficients in this particular format. So the coefficients of objective function in this table are -3, -9, and of course there is no s1 and s2 in this objective function, so we will put s1, s2 equal to 0 in this particular row. So again class, in this particular table we'll have to identify the condition of optimality. As I told you that in this particular problem we are interested in maximization, so we will check the condition of optimality, that all the coefficients of the objective functions should be positive. There should not be any negative value, but you can see from this row with respect to that objective function that we have some negative values. So it means that this table will not give you the optimal solution. So as a next step we will find out the highest negative value, which is actually the lowest overall value out of this objective function. So this is -9, which is the lowest value, and the corresponding column will be our pivot column, and this column will indicate that the x2 variable will be our entering variable. So we have identified our pivot column, we have identified our entering variable. Next we'll have to identify the pivot row, and again for computing or identifying the pivot row, what we will have to do, we'll have to divide this right hand side values with the respective pivot column values. We'll have two ratios. One ratio is for that S1 row, and the other ratio is that for S2 row. Class, in this particular case all of the two ratios are same, that is we have the ratio values for both of these rows equal to 2. Actually what we do in this particular step, we just ignore the negative values and the infinity values, and we just take into account the positive values. Then we will have to choose the minimum ratio value out of all the positive values available in this ratio column. But in this particular situation all of the two ratios are same, so we can take any of this row as the pivot row, because the values of both of these rows are same. Let's suppose we are taking this first row as the pivot row. You can always take the other row as the pivot row, so there is no difference because both of the values are same. if this is the pivot row, then 4 will be our pivot number because it lies at the intersection of the pivot row and the pivot column, and this particular row also helps us to identify the leaving variable. In this particular situation, S1 will be our leaving variable. So if we formulate the other table, what we will have to do, we will have to replace this leaving variable, that is S1, with the entering variable, that is X2 in this particular case. So after identifying all of these important value, if we go to the next table, so this is our next table. Now again class, I have omitted the different steps that how we got the values of this table. What you will have to do, again you will have to follow the similar procedure. We have already solved many problems using the different formulas, that is the formula for computing the new pivot row and the formula for computing the all the other rows. The formula for computing the new pivot row is equal to 1 over pivot number multiplied by old pivot row. So we will use this formula to identify and to find out our new pivot row, and again we'll have to identify all the other rows by using the other formula, that is any other new row will be equal to the old row minus pivot column coefficient multiplied by new pivot row. So by identifying and by calculating both of the pivot rows as well as the non-pivot rows, we will put all of these rows in this particular table. But at a first instant, first try to put the values of new pivot row in this particular table to replace the old pivot row position, and then as a next step, it's always better to put the non-pivot rows thereafter in this particular table to avoid any sort of confusion, So after computing this table, again we can see here that here basic variable S2 is 0, resulting in a degenerate basic solution. So that is one of the condition which we were discussing in degenerated solution, that अगर आपकी कोई भी बेसिक वेरिएबल की वैल्यू अगर 0 की इक्वल आ जाती है तो ये सिचुएशन ऐसी होती है विच इज़ रेफरिंग टू योर डीजेनरेटेड सॉल्यूशन. सो क्लास, अगर हम इसको आगे टेबल इसके बनाएं, नेक्स्ट टेबल बनाएं, जो भी हम देखेंगे इन द नेक्स्ट टेबल कि इसमें क्या सिचुएशन हमारे पास होती है. Now, as we discussed in the degenerated solution, that there may be chance कि जब हम इसका नया टेबल बनाएं तो आपका या तो ऑब्जेक्टिव फंक्शन रिपीट हो जाएगा या आपकी वैल्यूज रिपीट हो जाएंगी, एंड समटाइम्स द होल ऑफ द टेबल इज बीइंग रिपीटेड इन द नेक्स्ट कमिंग स्टेप्स. लेकिन जब भी आपके पास ये कंडीशन आए इस तरह की प्रॉब्लम्स में कि आपका कोई भी बेसिक वेरिएबल की वैल्यू 0 की इक्वल आ जाए, तो यू शुड हैव इन माइंड दैट देयर मे बी द केस ऑफ डीजेनरेटेड सॉल्यूशन. Now let's suppose that we formulate another table. You can see in this particular table the value of our objective function is equal to 18, but the condition of again the optimality is not satisfied in this particular table because still there is a negative value here in this objective function. So we'll have to identify this negative value as the pivot column because there is only single negative value in this objective function. So this will be our pivot column, and again we'll have to identify and calculate the ratios by dividing the right hand side values in this particular column by the corresponding pivot column values. We have the two ratios, that is 8 and 0. 0 is again the minimum value, and we can always take it as the pivot row. So 1/2 will be our pivot number, and again our entering variable and our leaving variable will be x1 and s2 respectively. So after identifying all of these important values, what we will do, we will have to formulate another table. So again class, we'll have to use the similar formulas, that is the formula for computing new pivot row and the formula for computing other rows. again you must have remembered now all of these formulas. I am putting that value directly in this particular table. So this is our new table. Now class, if you see this objective function, and you can see that all the coefficients of objective function in this particular row are positive. So it means the condition of optimality is satisfied here, but there is a point to be noted here, that in this particular case we have the maximum value of objective function as 18, but if we refer to the previous table, then you may know that we already have this value of objective function in our previous table. So this objective value is being repeated again in our table. So this is the situation of degeneracy, in which the same objective function may be achieved without any improvement, and a cycle is being started sometimes. And again, sometimes you can have the different tables, but you may not be able to improve your objective function value. So class, this is the particular case of that regeneracy solution, and you should be very careful about this sort of situation when you will solve the similar relevant problems. Now class, let's take this view of degeneracy problem from the other perspective. Now again, if we recall our objective function, we have some objective function, then we have two constraints in this particular case. Now if you recall your graphical method of solving the linear programming problems, what we do, that we convert those inequalities into the equalities, and then we draw those equations on the particular form, and then we try to find out the feasible solution. That is the solution which is feasible and which is fulfilling all of the different constraints. And again, after identifying that feasible solution, we may identify the optimal point on this graph at which our objective function may be maximized. So class, what we have done in this particular case, we have draw those lines for representing our two constraints. So these are the two lines. As you can see that this is the dotted area is your feasible region, and that is the area which is less than both of our lines, that is x1 plus 4x2 is equal to 8 and x1 plus 2x2 is equal to 4. So this is the feasible area which is less than both of these areas. But class, this bold line is our objective function. Again, if we take any arbitrary value of our objective function and we draw this line, so we can have the idea that at what point will be our objective function may be maximized. So this is that particular point which is actually the optimal point and which will give us the optimal solution. But the main point here in this graph is to be noted, that is with respect to our one of the constraint, which is now represented in the form of x1 plus 4x2 is equal to 8. Now what this constraint or what this line shows, that students, ये जो particular line है, ये हमारे इस ग्राफ में हो या ना हो, our feasible solution will not be changed. अगर हम इसको निकाल भी देंगे तो आपका feasible solution भी वही रहेगा और आपका जो optimal point है वो भी same रहेगा, और अगर हम इसको इस ग्राफ में include कर लेंगे तब भी आपका feasible solution भी वही रहेगा और आपका optimal line भी वही रहेगा. इस किस्म के जो constraints होते हैं, इसको हम sometimes कहते हैं redundant constraints, which does not make any difference. So this is actually the case of degeneracy problem, कि इसमें आपके पास जो recycling होती है वो बार बार सेम फंक्शन आपके पास आ जाता है जब हम ये पर्टिकुलर मेथड यूज करते हैं in order to find out the optimal solution. So this is what we discussed about the degeneracy problem, और हमने ये डिस्कस इसमें किया है कि किसी कैसे सिचुएशन जो degeneracy की अकर हो सकती है, और and you should have in mind that maybe that cycling may start and you may get the similar sort of objective function again and again. So class, this particular constraint, that is x1 plus 4x2 is equal to 8, it is a redundant constraint because its presence or absence does not affect neither on the optimal point nor on a feasible region. So this is the particular example we just discussed relevant to that degenerated solution. Next special case which may face while solving the problems, especially by using that simplex method, that is the alternative optimal. Now again, alternative optimal का concept क्या है students, कि sometimes ऐसा होता है कि हमारे पास बहुत से ऐसे alternatives available होते हैं कि अगर हम कोई भी alternative use करें तो आपके पास जो objective function है वो आपका same रहता है. So sometimes in certain situations and in certain problems we may have the infinite solutions, and again it is up to the manager कि वो इसमें से कौन सा alternative use करता है, लेकिन इन किसी भी alternative का आपके objective function पे या आपकी maximum value पे कोई भी effect नहीं होता. So this sort of situation is sometimes referred as alternative optimal. اور اس میں جب ہم ٹیبل بنا رہے ہوتے ہیں how we should have the idea that we may have this problem of alternative optimal if the f row value for one or more known basic variables is 0 in the optimal tableau, alternative optimal solution exists. Now again class, جو آپ کے پاس f row کی ویلیو ہوتی ہے, that is your actually objective function row, that is sometimes the last row of the table. اگر اس کی ویلیو اس کے کورسپونڈنگ جو ویلیو ہے کسی بھی نان بیسک ویریبل کی اگر وہ 0 ہو جائے تو یہ آپ کو ایک آئیڈیا دیتی ہے دیٹ دس از دی سولوشن آف آلٹرنیٹیو آپٹیمل. اور یہ ایک ایسی پرابلم ہے جس میں آپ کے پاس بہت سے سولوشن ہو سکتے ہیں, اینڈ آل آف دیز آلٹرنیٹیوز اینڈ سولوشن will give you the similar sort of optimal point as well as your maximum objective function. So when the objective function is parallel to a binding constraint, objective function will assume same optimal value. Now sometimes again جب ہم graphical method use کرتے ہیں in order to solve the linear programming problems, اس میں sometimes کیا ہوتا ہے کہ جب آپ objective function کو draw کرتے ہیں, you may remember کہ ہم ایک method use کرتے تھے graphical method میں, that is the iso-profit line method, جس میں ہم کوئی arbitrary value put کر دیتے تھے profit function میں, اور پھر ہم x1 اور x2 جو آپ کے decision variables ہوتے ہیں ایکچولی, اس میں ان دونوں کی values 1 by 1 0 put کر کے ہم دو points نکال لیتے تھے. ان دونوں points کو پھر ہم graph میں draw کرتے تھے in order to have that objective function line on graph. Sometimes ایسا ہوتا ہے اس graphical method میں کہ this objective function line becomes parallel to any one of the constraint. اگر یہ سچویشن آ جائے کہ آپ کی جو آبجیکٹو فنکشن لائن ہے وہ کسی بھی کانسٹینٹ کے پیرلل آ جائے, so this is the situation of that alternative optimal. اس کا مطلب یہ ہوگا کہ آپ کے پاس جو کانسٹینٹ کے اوپر جتنے بھی پوائنٹس ہیں اس لائن کے اوپر وہ سارے آپ کے optimal solution ہیں. So all the points which are available on this sort of a particular constraint that may give you the optimal solution. So this is the particular situation of that alternative optimal, and this is the situation when the value of the optimal objective function remains the same. By using the many infinite alternatives, sometimes we may have the similar objective function and we have infinite number of such points. So at all these infinite points you may have the same solution. Now again class, if you want to solve this particular problem relevant to this particular case we have just discussed, you can always solve this problem. That is, we have some objective function again, that is 2x1 plus 4x2, and this function is subject to the different constraints, that is x1 plus 2x2 is less than or equal to 5, and the other constraint is x1 plus x2 is less than or equal to 4, x1 x2 is greater than or equal to 0. Again, these are the known negativity constraints. Now again, if you want to solve this particular problem by using that simplex method, we'll have to use slack variables, that is x1 plus 2x2 plus s1 is equal to 5, x1 plus x2 plus s2 is equal to 4. So what we have done in this particular case, we have introduced the two slack variables, that is s1 and s2, for the first and the second constraint respectively, and now we have four non-negatively constraint variables, that is x1, x2, s1 and s2. Again, as an initial solution, what we will do, we will put the value of x1 is equal to 0, x2 is equal to 0 in order to find the value of our objective function, which is 0. Then s1 is equal to 5, s2 is equal to 4. So after that initial solution, we will have to put the values of coefficients in our initial tableau. Again, in this particular table, the first equation is x1 plus 2x2 plus s1 is equal to 5. There is no s2 in this first equation, so we will put s2 is equal to 0. Similarly, we will put the coefficients of the second equation as well as the relevant coefficients of our objective function after converting that objective function into homogeneous form. Again, this is very important, and after putting all of these values, we'll have to check the optimality condition. There are two negative values in this particular case, as we are discussing the case of maximization. So this table will not give you the optimal solution, because still there are some negative values in that objective function. So as a next step, we will identify the maximum negative value, that is -4 in this case, and this is your again the pivot column. And after dividing the values of that right hand side column with respect to the relevant values of a pivot column, we will have the ratio values as 2.5 and 4, and again this 2.5 is the minimum ratio, and the corresponding row will be our pivot row, and the value which is actually at the intersection of the pivot row and pivot column, this is our pivot number. And again, in this particular case, x2 is our entering variable and s1 is our leaving variable. Again, we will have to use the same formulas, that is formula for the new pivot row and the formulas for the other rows, and we'll have to compute another table. Now this is the next table. Again, how we have computed all of these values, that is again by using the similar formulas. I have not used and recalculated those values, by assuming that you all know that how to calculate the values of the new pivot row and the values of the other rows. Again, we use the same formula for the new pivot row, that is 1 over pivot number multiplied by the new old pivot row, and again the formula for the any other new row will be equal to the old row minus pivot column coefficient multiplied by new pivot row. So after calculating and computing these pivot row and the non-pivot rows, we will put all of these rows in this particular table. So class, now we have all the values equal to 0 or positive in that objective function. Here in this particular case, if we consider the values of x2 is equal to 5 by 2, and as there is no value of x1 in this basic variables, so we can take the value of x1 is equal to 0, then we can get the objective function equal to 10 in this particular case. So if we compute another table, again by computing that new pivot row and by computing all the other rows by using the similar formulas, we can have this sort of table. If you see this table, we have the idea that again we have the same objective function value, that is 10. In this table, the function of the value of our objective function is equal to 10. In the previous table, again the value of the objective function was equal to 10, but here the alternative was different. Here we were putting x1 is equal to 0 and x2 is equal to 5 by 2, and both of these values give us the optimum solution as 10. But in the next table, if we put x1 is equal to 0 and x2 is equal to 5 by 2, in this table if we put x1 is equal to 3 and x2 is equal to 1, again we will get the same optimum solution, that is 10. So here you have the idea that we may have some multiple alternative solutions which may give you the same value of objective function. So this is the special case of alternative optima we were discussing, that there may be the situations and there may be the different alternatives available before the operations manager, that by using any of the alternative, he or she may have the similar objective function and the similar maximized value or the minimized value, and it is up to the discretion of the operation manager that which particular alternative he should use for his particular scenario. Again class, if we represent this problem in the form of that graph by using the graphical method, we can have this sort of graph. Now these two equations are constraint equations. Of course we'll have to convert those constraints or inequalities into the equalities, and by using that method of identifying x1 is equal to 0 and then x2 is equal to 0, we may have the 2 points. In order to draw these lines, we have already discussed this method in graphical method of problem solving. So this is the point C is the point of intersection for these 2 lines. Now again class, if we recall our iso profit line method for drawing that profit line on this graph. So what we do in this particular case, we put the profit value up to any arbitrary value, and then by putting values of our decision variables one by one equal to 0, we may have a sort of line which may be drawn on this particular graph. Now in this particular problem, this is our iso profit line. Now class, you can easily see that this line of profit is parallel to one of the constraint. This one is the constraint, and both of these lines are parallel. And again, please recall one of the method to find out the optimal point by using that graphical method. What we do, we move this profit line away from the origin so that it may touch any of the extreme point within that particular region, that is the region of our feasibility. Now this dotted region is represented here as our feasible region. Now class, if we move this line parallel or above to the origin, the line of profit will become lie on a particular constraint. Again, if we move this line of profit towards our constraint, this profit line will lie actually on one of the constraint. So this was actually the situation which I was discussing, that in certain cases when our objective function line becomes parallel to any of our constraint line, then this is the situation which is referred as alternate optimum. اور اس کیس میں اسٹوڈنٹس ہوتا کیا ہے کہ جب یہ لائن اس کے بالکل اوپر لائی کرتی ہے، اس کا مطلب یہ ہوتا ہے کہ اس کانسٹینٹ کے اوپر جتنے بھی پوائنٹس ہیں، اس میں ہم کوئی بھی کمبینیشن یوز کر رہے ہیں اپنے ڈیسیژن ویریبلس کا، تو آپ کا جو پروفٹ کی ویلیو ہے، میکسیمم ویلیو جو ہے وہ آپ کی سیم رہتی ہے. سو دس از دی پرٹیکولر کیس آف آلٹرنیٹیو آپٹیمم. And again I will repeat it, that all of the values which are lying on this particular constraint, which is actually parallel to the profit line, will give you the optimal solution. Now it is again up to the discretion and choice of the operations managers or the general managers that which particular alternative they should use with respect to the particular scenario or some objective. In practice, alternative optimals are useful as they allow us to choose from many solutions, experiencing deterioration in the objective value. So class, in this particular case, again, we may have the different solutions, and we may select one of the solution in order to find the value of the objective function, because the usage of the either of the solutions will not change the value of the objective function. So this is our second case about alternative optimal. Now let's discuss our third case, that is referred as unbounded solution. When determining the leaving variable of any tableau, if there is no positive ratio, all the entries in the pivot column are negative and zeros, then the solution is unbounded. Class, please recall the different steps which we usually follow in order to compute that initial tables and further tables by using that simplex method, either in the case of two-phase method or in the case of big M method. In this particular method, what we do, we have to calculate sometimes the ratio column, that is the column achieved by dividing the right hand side values with respect to the corresponding pivot column values. اور اس میں اسٹوڈنٹس ہم نے یہ ڈسکس کیا تھا کہ جو ریشوز کی ویلیوز جو ہیں اگر نیگیٹو آ جائے یا انفینیٹی آ جائے تو اس کو ہم اگنور کر دیتے ہیں, اینڈ وی ول جسٹ ٹیک ان ٹو اکاؤنٹ دی پازیٹیو ویلیوز. لیکن اگر آپ اس قسم کی پرابلمس سولو کر رہے ہوں اور آپ کے پاس اگر کوئی نیگیٹو ویلیو آ جاتی ہے یا آپ کے پاس کوئی انفینیٹی ویلیو آ جاتی ہے, and there is no other value which is positive ratio available in this particular column, then that particular situation is referred as unbounded solution. So ہمارے پاس جو ریشیو کالم میں سب ویلیوز ہوتی ہیں وہ یا تو نیگیٹو ہوتی ہیں یا انفینیٹی ہوتی ہیں, and this is the situation in which sometimes we cannot find out the optimal solution, and this particular situation is known as unbounded situation. Again, class, let's take the example of this unbounded solution. Let's we have a function and we are interested to maximize this function 2x1 plus x2, and this is subject to the different constraints, that is x1 minus x2 less than or equal to 10, 2x1 less than or equal to 40. These are the non-negativity constraints. Now again, we'll have to introduce the variables, that is the slack variables. Let s1 and s2 be the slack variables in this particular case. Now we have two equations by introducing that slack variables. This is our initial solution. Now class, after the initial solution, if we put the coefficients values of these equations in this particular table, we can get the initial tableau of this particular problem. And again, because we are interested in maximization, we'll have to check the optimal condition that all the coefficients of the objective function should be positive. There are two negative values in this particular case, and this is the maximum negative value. So this will be considered as your pivot column, and after identifying the pivot column, you'll have to identify your pivot row. For that particular reason, we'll have to calculate the ratio values, and we'll have to divide that 10 by the corresponding pivot column value, that is 1. So we'll have the two ratios in this particular case, that is 10 and 20. 10 is the minimum value out of these two values available in this particular column. So this will be our pivot row, and 1 will be our pivot number. And this pivot row and pivot column also help us to identify that x1 is our entering variable and s1 is our leaving variable. So after computing the particular values of new pivot row and other new rows by using the different formulas we have already discussed, we will have this sort of table again. And again, in the objective function, you can see that we have a negative value, and again we'll have to reformulate this table by computing the new pivot row and by computing all the other rows by using the relevant formulas, of course. Now class, this is our next table, and in this particular table you can see that if this is your pivot column, if we cannot compute the ratio values in this particular case, because because all the values in this particular ratio column will be either infinity or negative. So this is the situation we always have to ignore, and this was the situation we were talking about as the unbounded solution. So this is the particular case of unbounded solution, and what actually happens in the unbounded solution, the values of non-basic variables are either 0 or negative, and the solution space is unbounded. So یہ پرابلمس اس قسم کی پرابلمس ہوتی ہیں کہ ہمارے پاس کسی ایک ویریبل کے لیے جو سولوشن اسپیس ہے وہ انباؤنڈیڈ ہو جاتا ہے، یا اس کی ویلیوز اگین گوز ٹو انفینٹی، وائل دی ادر ویریبل جو ہوتا ہے اس کی ویلیو آپ کے پاس 0 ہو جاتی ہے. سو یہ وہ سچویشن ہوتی ہے جس کو ہم کہتے ہیں انباؤنڈیڈ سچویشن. And again, if we draw this particular problem by using that graphical method, so this is our constraint, and this constraint is actually the 2x1 less than or equal to 40. So this will be our feasible area for this particular constraint, and it actually represents the unbounded solution space for this particular case. And this is our second line, that is x1 minus x2 is less than or equal to 10, and of course the area less than to this line will be the feasible area for this particular line. But again, we are interested in the feasible area which is less than for both of these two constraints. So class, this is our objective function, and this is our optimal point. So in this particular case, what happened, that we have unbounded solution space for this particular constraint. So this is the situation which is referred to as unbounded solution. So this is the third case which we have discussed about simplex method problems. The next special case is infeasible solution. As its name shows, that this is a sort of situation in which we are unable to find any of the feasible solution because of the different reasons, because we may have the different constraints which may not be able to fulfilled, and it is not always possible to meet all the limitations and constraints in the particular scenarios. So this sort of situation is usually referred as infeasible solution. A problem is said to have infeasible solution if there is no feasible optimal solution is available. So this particular solution is referred to as infeasible solution. Now class, again, this is the example of that infeasible solution. This is our objective function. It is subject to the different constraints, and again, if we draw these constraints on this graph, you can see this is the line of our one of the constraint, and this is the line for our second constraint. Now what is the feasible area for this particular line is the area which is above that line, because it is represented as greater than equal to a form of inequality, and the feasible area for this particular line which is less than that particular line, because it is represented as less than equal to inequality. So class, in this particular case you can see that we cannot find any common points, that is the area which is common for both of these lines. In this particular case we cannot find out any of the feasible area. So this is the particular situation or the particular solution which usually refer as infeasible solution. So infeasible solution is a sort of situation in which we cannot get any of the optimal solution. So class, in our 15th lecture we discussed the different special cases related to the linear programming problems, and especially the different cases which you may face while solving the different sort of problems, and these situations you must always keep in mind when you are going to solve these particular problems. I have taken almost 4 to 5 lectures for that linear programming problems. This is so important topic in operations management, and now we have done enough questions relating to that linear programming by using either by the graphical method or the two-phase method or Big M method. And of course you must have enough practice of solving these sort of problems, and please be very careful in your final examination, as this is a very important topic with respect to your midterm as well as with respect to your final term examination. And always try to solve the similar problems from some other books, as well as you can take some problems from the net, and it will always be good for you people to solve the similar problems by using the different methods, so that you should have enough practice for solving the linear programming problems. So this is the end of our today's lecture, and in the next lecture we will discuss another important technique, that is the transportation problems. See you class in the next weekend. Take care. Khuda Hafiz.